This video is about solving linear inequalities. And in the context of this topic, we're going to be using something called interval notation. And so to connect that with the typical inequality symbols, if we have a strictly less than or greater than, that's going to translate to a curved parenthesis for the boundary symbol of the interval. If we have an inclusive less than or equal to or greater than or equal to, that's going to translate to squared brackets. And in either case, the parenthesis or the bracket will open toward the arrow in the context of a graph, a number line graph. So that notation will be used throughout this topic. And let's get in with some examples which say solve, graph, and write using interval notation. So again, there's that notation we just kind of reviewed in its symbolic components. Our first example is an inequality that begins as follows. 8x plus 3 is greater than 3, open parenthesis, 2x plus 1, close parenthesis, plus x plus 5. Now, let's remember one key thing about inequalities, and this is not new. So we're in the context right now of an intermediate algebra course, but the idea of an inequality is usually introduced before this. So as a means of review, let's recall this. Solving inequalities is just like solving equations, except there's one exception. If we multiply or divide by a negative, we must flip the inequality symbol. So we always have to keep that in mind anytime working with an inequality. However, other than that one exception, solving an inequality is just like solving an equation where you want to get the variable alone. So in this problem, we want to get x alone, and we'll do all of our typical steps, which would involve distributing this 3 first into the parentheses. So if I recopy the whole thing, on the left side I'll have 8x plus 3 is greater than, and then after distributing the 3 I'll have 6x plus 3, and then plus x plus 5. Next, of course, we'll go ahead and combine like terms. On the left side there isn't anything to combine, so we'll leave that as 8x plus 3, keep the greater than as is. On the right side, notice we have a 6x plus an x. We could combine to get 7x, and then a plus 3 and a plus 5 would be a plus 8. And then at this point, I like to emphasize the strategy of dealing with variables first and then going smaller to larger. It helps to avoid some negative issues that arise if we're a little careless with the order in which we approach the next steps here. So if I take the variable terms first, that would be the 8x and the 7x, and I move the smaller one to the larger one, which would amount to subtracting 7x from both sides. Then the 7x is canceled on the right side. On the left side we have 8x minus 7x, which would be just a 1x or an x. And so now we have x plus 3 on the left side, greater than, and then just an 8 on the right side. Now we want to get x alone, so we'll just subtract the 3 from both sides, which will leave us with just an x on the left side is greater than. On the right we have 8 minus 3, so 5, which means we've now gotten x alone, which was our goal to solve this inequality. So x is greater than 5 would be the inequality solution. Now, we want to turn that not only into a solution, remember there was 3 steps. Solve, we just did that. Next we want to graph, and then write using interval notation. We can go from the solution we just got to a number line graph simply by putting out a number line and then putting our boundary number of 5 on the number line. We don't really need much else with it. You don't have to get too carried away with the number line and add a whole bunch of other values. The boundary number is good enough. And then we want to convey a number line graph that represents all these x values that fit within the solution. Let's also remember that the inequality symbol is not an arrow, it's an alligator eating the bigger value. Okay, I know it sounds silly, but it actually is a more reliable way to understand the symbol, and it avoids a lot of the common troubles that students will get into with this symbol. So if it's preferring to eat the x, that means x is bigger than 5. And on the number line, a bigger than 5 would be to the right of 5. So we're going to have an arrow starting at 5 and then going to the right from it on the number line. And then we simply use the boundary symbol that coordinates with the symbol notes we put way above. So in this example, we have a strict inequality where the x is strictly greater than 5. That translates to a parenthesis that's opening toward the arrow. So we have a right-facing parenthesis right on the boundary number of 5. This is the interval notation symbols used in the number line graph, which is what we want. Now, thirdly, as mentioned above, we want to turn this into an interval notation, which is just a summary of the number line graph itself. So we're going to take the left boundary, which is a 5 with a parenthesis, and simply write that out. So a 5 with a left, or a parenthesis opening toward the 5. So the parenthesis is to the left of it, kind of hugging the 5. Then we put comma, that's the left boundary. The right boundary, because of this arrow on the graph, would actually be infinity. It just keeps going. So on the right side of the comma, we put the infinity symbol, the sideways 8. And we always put a parenthesis around infinity or negative infinity because you never quite get there to make it an inclusive boundary like the bracket would be. So we'd simply put 5 comma infinity in a set of parentheses for our interval notation. And so now all of this amounts to our solution, including the graph and the interval notation for this inequality. Let's try another example. This one begins as, on the left side here, 3x over 10 plus 1, and then greater than or equal to 1 over 5, 1/5, minus x over 10. Now, in an example like this, we still want to bring in the tricks we know for equation solving. And for something like this, we would typically, if it were an equal sign, be probably more inclined to notice here that we should really clear these fractions. So I'm going to put a little note. Let's go ahead and clear fractions, which we're still going to do in the context of an inequality. It's the same process. And so we need to find our LCD for all the fractions in the whole problem, which would be ultimately 10, the least common multiple of 10 and 5. And we're going to multiply all the terms by that LCD, which is the process of clearing the fractions. Now, in this case, as we would for an equation, I'm going to write out each original term, but put it in a set of parentheses and leave a little extra space surrounding all this. And so really I'm just copying the original problem down, putting all the terms in parentheses, and then we're going to go back through and take this LCD that we've decided already, this 10, and we're going to put that scattered throughout. If I were to take this LCD of 10 and multiply by it for every term all the way across, that's the process of clearing the fractions. Notice that if this is a positive 10, we're multiplying by all the way through, which means we don't have to adjust the inequality symbol. Now we should be mindful of that because chances are if you're multiplying something all the way through an inequality, if that value is negative, which it could be, then you would have to change the sign as we noted way above. So we're simply multiplying by positive 10 all the way through, which means we'll just go through and reduce each fraction. So we have 10 over 10 that cancel in the left term, giving us just a 3x, plus, then we have a 10 times 1, which is 10. Keep the greater than or equal to. Moving on, we have 10 over 5, which is really just 2, and then minus, and then the 10s cancel in the last term, giving us just an x. So clearing the fractions can be a great step because it eliminates the fractions and makes it, I think, simpler to see the path forward. At this point, we'll use our variables first, smaller to larger trick, and in that decision, add x to both sides. So the x's cancel on the right side. On the left, we're left with 3x plus x, which is 4x. Then we have plus 10 is greater than or equal to 2. We'll continue on with this by subtracting 10 from both sides. This will give us 4x is greater than or equal to, we have now 2 minus 10, which would be a negative 8 on the right side. But to get x alone, we'll have to divide by 4 to finish. Notice we're dividing by a positive 4, which means we don't have to flip the inequality sign. Even though on the right side we have the negative 8, that's no problem. The number we're dividing by is positive. So in fact, negative 8 over 4 is negative 2, which gives us our inequality solution. X is greater than negative 2. So we'll take that directly to a number line where we'll put the boundary number of negative 2 on it. And if x is greater than, according to this symbol, that means it's to the right on the number line. So we'll put an arrow to the right, and then this time, since it's an inclusive greater than or equal to, we'll put a square bracket on the boundary opening toward the arrow, and that would account for the graph. Now the interval notation is just the summary of the graph with its endpoints. So we put our left boundary of negative 2 with its boundary symbol of the bracket, comma, and then the arrow on the right side would indicate a positive infinity. So we'll just put infinity with a parenthesis surrounding it to the right side as well. And so there is our graph and our interval notation representing this solution to the inequality. Let's try yet another example. This one begins with a fractional term first on the left side. The numerator is 4x minus 3, and it's all over 6. Then we have plus 2, and then that's greater than or equal to. On the right side, we have a fractional term, which is 2x minus 1 in the numerator, all over 12. Well, kind of like we just did in the previous example, this would be a good case for clearing the fractions. And so let's go ahead and just put a note to remind ourselves we want to clear fractions. Of course, to do so, we want an LCD. And given the only denominators here are 6 and 12, the LCD would be 12. So like we did before, we're going to write out the original problem. I'm just going to copy it down. So we have 4x minus 3 all over 6, but I'm going to put that in a set of parentheses. Leave some space, then we have plus, and then we have 2, which I'll put in parentheses as well. And that's greater than or equal to. On the right side, we have a term in parentheses, which is 2x minus 1 in the numerator all over 12. And then we go back through with our LCD of 12 and multiply it by every term on both sides. When doing this, the whole point is to reduce the fractions. So we have 12 over 6 in the first term on the left side. Those are reduced to 2 over 1. But then we're going to have to distribute this 2 that we get by reducing into the terms inside the parentheses. Be careful not to forget that. That will give us a result of 8x minus 6. And then continuing on, we should say plus 24, the 12 times 2. That's greater than or equal to, on the right side now, we'll cancel the 12. So there's a 12 over 12. Those are gone, leaving us with only what was in the numerator inside the parentheses, which is the 2x minus 1. Okay, so we're on our way to getting x alone, which is the main task in solving the inequality. We have one set of like terms to combine, that is these numeric terms on the left side, the negative 6 plus 24. So we'll do that and rewrite this as 8x and then plus 18 to combine those terms is greater than or equal to 2x minus 1. At this point, we'll go variables first, smaller to larger, and so I'll decide to subtract 2x from both sides. That'll give us a 6x plus 18 on the left side is greater than or equal to negative 1. We're almost there. Let's subtract 18 from both sides so that we end up with 6x is greater than or equal to negative 19. And then we'll divide by 6 on both sides to get the x alone. Of course, it's a positive 6, so we don't have to flip the inequality symbol. We are left here at the end with x is greater than or equal to negative 19 over 6, which isn't very pretty, but there's no way to reduce it, so we'll just leave it as is. And then we can turn this into a graph by simply taking that boundary number and putting it on the number line, so negative 19 over 6. And x is greater than or equal to it, so it's going to the right with a bracket given that kind of boundary. And so there's our solution and graph. The interval notation would be the summary of the graph, as we've been seeing. So a bracket with a negative 19 over 6, as the left boundary, comma the right boundary, which again here is an arrow to the right, which would be a positive infinity with a parenthesis. So infinity always gets a parenthesis, whether it's positive or negative. A couple examples here have ended up with a positive infinity, but you could very well get a negative infinity as a boundary on the left side if the arrow is pointing to the left. And in that case, you would put a negative infinity as the left boundary with a parenthesis surrounding it as well. Let's try yet another example. This next one begins as 5x is less than, and then on the right side we have 5, open parenthesis, x minus 3, close parenthesis. So let's go ahead and start by distributing the 5 to both the terms in the parentheses, which would result in a 5x is less than 5x minus 15. But then to follow our typical steps of going variables first, smaller to larger, let's go ahead and subtract 5x. Now, of course, there isn't a smaller x term. They're both 5x. Notice, though, but if I subtract 5x from both sides, both of them cancel out, leaving us with a 0 on the left side is less than. On the right side, we have just a negative 15 left over. But that's interesting. There's no more variable involved, and what we're left with is actually not true. 0 is not less than negative 15. So what's going on? Well, when the variables disappear and we're left with something that's false, which I will note here, false, we would have to say that there is no solution to this inequality. There wouldn't even be, therefore, a graph that goes with it. There's just no solution, therefore no graph, and no interval notation either. Let's try another example. This one begins as 2 over 7, open parenthesis, 7 minus 21x, close parenthesis, minus 4 is greater than, and then we have on the right side of the inequality 10 minus 3 over 11, so 3/11ths, and then in a set of parentheses following that, 11x minus 11. Okay, well, there probably are a number of ways you could approach this problem. My suggestion would be that if you have a scenario where you have these fractions in front of parentheses that follow them, instead of trying to clear the fractions right away in this scenario, which you actually could do, but it's more risky and usually mistakes start happening in that, I recommend distributing these fractions before we try to clear any fractions. So let's go ahead and do that. If I distribute the 2/7 into the parentheses, 2/7 times 7 would be just 2. And then going to the next term, 2/7 times negative 21 would be negative 42/7 x. Then we have a minus 4, we're just carrying down, and that's all greater than. On the right side, we're going to copy down our 10, but then to distribute the 3/11ths into the parentheses, it's a negative 3/11ths, that is, we have 3/11ths times 11x would be just 3x. So we'll say minus 3x, and then on to the last term, the 3/11ths times the negative 11 would end up as a positive 3. Okay, so again, it's a negative 3/11ths that's getting distributed in there, so that negative sign is changing the signs of those terms inside. Now we'll try to combine like terms. There's a little more to do just to clean this up. On the left side, we have a 2 and a negative 4 to combine, so we'll just leave this negative 42/7 x as it is, but then combining those other terms, we'll have a minus 2, and that's greater than. On the right side, we'll have, we can combine the 10 and the 3 to get 13 minus 3x. And then, of course, we could have maybe done this at the previous step, but 42 over 7 is actually 6. So this is really negative 6x minus 2 is greater than 13 minus 3x. And we could now go variables first, smaller to larger. Be careful on these. The smaller of these two variable terms is actually a negative 6x, since they're both negative, the negative 6 and the negative 3. That can be a little tricky. And again, this isn't the only way to approach these, but my suggestion of taking the variable terms first and going smaller to larger usually prevents negative sign mistakes that occur commonly. So let's go ahead and add 6x. That's actually moving the smaller variable term to the larger one. So the x's cancel on the left side, leaving us with a -2 is greater than. On the right side we have 13 and then plus 3x. And to get this further, we'll subtract 13 from both sides, which will leave us with a -15 on the left side, but that being greater than 3x on the right side, and then we can finish by dividing by 3 on both sides. Okay, so let's write the result over on its own. On the left side we have -15 over 3, that's really just -5. And that's greater than, notice we divided by a +3, so I don't have to change the inequality symbol by flipping it. And on the right side, we now just have the x. All right, well, that can be turned into a number line graph simply by putting a number line and putting -5 on it. And this time, remember, the hungry alligator wants to eat the -5, which means the x is smaller, which means it's actually to the left of -5. So our arrow this time is going to point to the left, and it'll be a strict inequality, so a parenthesis. So that's our graph going with this solution. And of course, the interval notation would be a -infinity on the left boundary with parentheses, since the arrow goes to the left, comma, and then a -5 is the right boundary with a parenthesis, which matches the graph. And so here's our solution and our graph and our interval notation going with this inequality.